The first half of question 7 is about minimum spanning trees. So we're given this network here, and it's basically each node is a waterfall, and each edge is the distance it takes to walk from one waterfall to the other. And now they want to plan a route which allows the visitors, to see every waterfall while moving through the park without wasting time. So in order to do that, we have to find the minimum spanning tree. So you can use whatever algorithm you want. I'm going to use Kruskal's, just because it's the one I prefer, and I think it's easier to show the workings out. So we're going to write down each edge and its weight from smallest to biggest. So I've written down all the edges from smallest to biggest, and now we're going to go through each one, and we're going to add it to this minimum spanning tree, and if it makes a cycle, we're going to skip it. So starting off with the HF, which is 4, so I'm going to draw on the diagram just so we can see what's happening. So that's good, we'll put a tick beside that. HJ is also good, we'll put a tick beside that too. CD is 7, and that doesn't create a cycle, so we can put a tick beside that. JI also doesn't create a cycle, so tick. LK also doesn't create a cycle, tick. CE also doesn't create a cycle, tick. KI also doesn't create a cycle, tick. CF doesn't create a cycle, tick. EG doesn't create a cycle, tick. EH would create a cycle, because then we could go, if I draw it in, you can see there's like a little closed loop here around this area. So we're gonna skip EH, so put an X to show your workings that you're skipping this one. AD is 11, and that's fine. That doesn't create a cycle. Tick. GJ would create a cycle, so we put X. FI would create a cycle, so X. GL would create a cycle, so X. And BE is the final one, and it does not create a cycle, so tick. Now, to double check that we've done everything right, we can see that there is an edge touching every single node, and there are no cycles, so that means we did it right. Now, part 2 is a little weird, and I'm actually not exactly sure how they want you to do this, but it says that the entrance is at waterfall A and the exit is at L. Using your minimum spanning tree, calculate the time needed to enter the park at waterfall A, visit every waterfall, and leave the park at waterfall L. And the reason I'm not sure for this is because if you have a look at our minimum spanning tree, if you're going around trying to visit all the waterfalls, you're going to backtrack yourself. For example, up here, you're going to have to go from C to E, E to G, then back from G to E, then from E to B, then back to E, and then back down to C. So it turns out that using this minimum spanning tree actually doesn't give you the shortest time to visit every waterfall, but because they said to use your minimum spanning tree, we'll do it anyway. And just imagine we're starting at A, so we start at A and we go down to D, so that's 11. I'll write this at the bottom, 11. Then we go from D to C, that's fine, plus 7. Then we go from C up to E, so that's plus 9. Then we go from E to G, which is plus 11. Then we have to go back from G back to E, so that's plus another 11. Then we have to go from E to B, which is plus 16. Go back from B to E, which is another 16. Then go back from E to C, which is another 9. Then go from C to F, which is 10. Then go from F to H, which is 4. Then go from H to J, which is 6. Then go from J to I, which is 8. Then go from I to K, which is 10. And then go from K to L, which is 9. I think that's how they want you to do it, but again, there is a shorter way of doing it, but since it says use your minimum spanning tree, I'm guessing this is the way to do it. Some people thought you just you just find the length of the minimum spanning tree, you just add up all the weights, but that doesn't make sense, because if you go to B, you can't go straight all the way over to G, you have to go back through E first, but this is the way I thought it made sense to do. So you add all those up, and you get 137 minutes. And I suppose if you wanted to show your workings out, you could also say you go from A, D, C, E, G, E, B, E, C, F, H, J, I, K, L. Just say the route that you're taking so that they know where you got the numbers from, maybe. The next one was a differential equation. I don't need to read all that. Basically, you have the differential equation there, and we just need to solve it. So first thing I do is I divide both sides by 2000 minus n to get the n's on the same side, and then multiply by dt to get rid of that. So we look at dn over 2000 minus n. That's going to be equal to k dt. Now what I'm going to do is, I notice if we integrate the left side now, we're going to have that minus n, so we're going to have to do a u substitution. But if we actually get that to be a positive n, we wouldn't have a u substitution, because if you think about it, let u equals n minus 2000, for example, then du is just equal to dn, so we don't have to do the substitution. So I'm actually going to multiply by minus 1, so we'll get minus dn over n minus 2000 equals k dt. Now we can integrate both sides, so we can take the negative out the front, get minus the integral, and since we're not messing around with substitutions and stuff, I'm just going to plug in the values. So n starts at 250, and it goes up to some value of n that we're trying to find, and that's going to be of dn over n minus 2000. It's going to be equal to the integral from time starts at 0 up to some time t of k dt. So for n, because there's the derivative of n minus 2000 is just 1, we don't have to worry about substitutions, as I said, so we can just do this as normal. So we're going to get minus ln of n minus 2000, and that's evaluated from 250 up to n, equals the integral of k dt. K is just a constant, so it's just going to be kt from 0 to t. So then we'll get minus, and then we're going to have ln of n minus 2000, and then we're going to have minus, and then replace the n with 250, ln of 250 minus 2000. That's going to be equal to kt minus 0, which is just 0. So now we can distribute that negative, and we'll get ln of 250 minus 2000 minus ln of n minus 2000. We can combine those into one ln by writing ln. We're going to have this one's the positive, so 250 minus 2000. So it's going to be minus 1750 over n minus 2000. And that's going to be equal to kt. Now we're looking for an expression for n. So we can do e to the power on both sides. So they'll cancel, and we'll get minus 1750 equals e to the kt. And sorry, that minus 1750 is still over n minus 2000. Now multiply by n minus 2000 divided by e to the kt. We get n minus 2000 equals minus 1750 over e to the kt. Then bring the 2000 to the other side. N equals 2000 minus 1750 over e to the kt. And that's our equation. In part 2, we're told that after 6 hours of learning, the student is able to spell 1,500 of these words, calculate k. So that's basically saying when t is equal to 6, n will be equal to 1,500. So I'm going to go back up to here, and if you see this point here, it's actually easier to solve for k, because if we used the final equation, we'd have to do a bunch of simplifications to get k by itself. So we're just going to actually use this part. So if we just divide by t, we'll get 1 over t, which is 6, times the ln of minus 1750 over n is 1,500 minus 2,000. And that's going to be equal to k. Put that into your calculator, and you'll get the k is approximately equal to 0.209. So in the last part, we have to graph this function of n against t to show the prediction for the student's learning curve. So there are two ways you could do this. You could either plug in the numbers into the equation and do it in fives. I just did it in fives because that's what they gave, but it doesn't really matter. Or most calculators have a table function, and that'll actually do it all for you and put it in a little table. So I did that on my calculator, and I just wrote it out here. So we can just plot the points. So then once you plot all the points, you can just connect them together and make sure it's kind of curvy, because as you can see, it's not linear. It's a type of exponential curve, so it's going to curve. It's going to kind of level off as we go up. So it's not perfect, but something like that, if you use a ruler at the end,